Welcome to Part 2 of On Landings, the program that explores typical problems we all might encounter during the landing phase. In Part 1, we discussed the classic killers, the undershoot and the cross-control stall. And we also looked at the hard landing, the bounced landing, or pilot-induced oscillation, and loss of directional control on landing. In Part 2, we're going to look at two kinds of landing accidents that tend to complement one another. By that I mean that in some cases, if the first one don't get you, then the next one will. The two are landing long and the poorly executed go-around. Let me begin by asking you a question. When was the last time you looked at the landing performance charts for the aircraft you fly? We all know that you certainly can't take the time to study them when you're acting as pilot in command. But when was the last time you studied these charts in a relaxed environment? You really can't afford not to, you know. They're just too important. And if you can't take them home with you, schedule some extra time before your next flight to go over them. Aircraft performance charts are presented in one of two fundamentally different formats: the graphical and the tabular. This particular example of the graphical format shows the landing ground rollout distance under various conditions. And here is an example of similar data for another aircraft presented in the tabular format. This particular performance chart provides both landing rollout distance and total landing distance. Total landing distance, by the way, is the landing distance from a 50-foot obstacle to a full stop. Notice that in the tabular format, pressure, altitudes, and temperatures which are not listed can be obtained through interpolation. Make sure to check your performance charts for conditions and notes as well. This supportive information can also have a very important impact on aircraft performance. Here, for example, we're told that landing on dry grass requires a ground roll that's 40% longer. And notice these associated conditions: flaps 40 degrees, power off, paved, level, dry runway, full stall touchdown, and maximum braking. Some performance charts provide different approach speeds for different landing weights, while others only provide the maximum landing weight approach speed. Now stop for just a minute and imagine yourself coming in. You're flaring, and now you're touching down, and now you're rolling out, okay? All right, now, watch that rollout in your mind. Okay, here's a little quiz. Make a mental list of all the factors you can think of that can affect the length of your landing rollout. Make a mental list of all the factors that can affect the length of your landing rollout. All right, time's up. Let's see how many you thought of. Now, I'm sure all of you thought of landing speed. And most of you probably said landing weight. That's very good. You might also have thought of wind. Wind is a very important factor. And another you've probably remembered is density altitude. That's the combination of pressure, altitude, and temperature. Density altitude isn't as important for landing as it is for takeoffs, but it's a factor all the same. But did you also remember that runway slope is a factor? And how about the runway surface? Is it bumpy or smooth? Hard surface or grass? Wet or dry? It's important to know because it can have a substantial impact on another factor that you may not have remembered, and that is braking. That's right, braking. I'm talking, of course, about the pilot's braking techniques, your braking techniques. Oh, yes, and how about the runway length? Sure, runway length doesn't affect your landing rollout, but where you locate your aim point does, especially if it's too far down the runway. These are the 8 factors that must be thoroughly understood and controlled in order to avoid the hazard of landing long. So now, let's look at each of them in detail, beginning with mastering airspeed control. Mastering airspeed control is the most important factor in achieving landing precision. Precise control of your airspeed during the landing phase is the key to touching down and stopping the airplane where you want it, and not landing long. Achieving precise control of your landing speed begins in the traffic pattern. It begins with the concept of a stabilized approach, something we discussed in detail in Part 1. You can begin mastering airspeed control by going back and checking the numbers. You should know and use the appropriate airspeeds for each segment of your approach: pre-pattern, downwind, base, final, and short final. And if you can't locate all of them in the aircraft's existing paperwork or on the placards, try to get them from a flight instructor experienced in your specific make and model. For example, when you're on short final with wings level, you should be flying at the published approach speed recommended by the manufacturer. If for whatever reason that speed is not known, then the rule of thumb is to set up a short final approach speed of 1.3 VSO. Now let's take time out here for just a minute to talk about what I mean when I say VSO. For the purpose of this discussion, VSO refers to the calibrated power-off stalling speed of an airplane when it's in its landing configuration, and usually with the center of gravity, or CG, as far forward as the envelope permits. And since that's what VSO is, then it's reasonable to assume that 1.3 VSO is a speed that is 30% greater than the VSO. Okay? Now, we've said that if the manufacturer's recommended final approach speed is not available, use 1.3 VSO. We can think of only 3 instances where this rule is not valid. So before going on, let me tell you what they are. The first is when you're flying a twin. Then you should be at the manufacturer's recommended final approach speed, or if you don't have that speed available, VYSE, the best single-engine rate of climb airspeed, a value which may be greater than 1.3 VSO. The second is when strong, gusting winds are present. We'll address that problem when we talk about winds in a few minutes. And the third is when you're trying to land with an unwanted load of ice. Under such conditions, your stall speed will be much higher, and you've got to carry extra airspeed. However, carrying extra airspeed on short final for any other reason is like carrying a false security blanket, and you're only creating an invitation to land long. And don't think it's going to do any good to force it on at higher than recommended airspeeds either, just so you can say it's on the runway. Let me tell you why. Rollout distance is increased by the square of the ratio of the actual touchdown speed to the normal landing speed. So, if an airplane that's supposed to be landed at 50 knots is planted at 55 instead, and we're talking about forcing it on the runway at a 10% higher airspeed, now that 10% increase in airspeed is going to require 21% more distance on rollout, assuming that all other factors are equal. Okay? Remember now, we're talking about ground rollout distance here, not total landing distance over a 50-foot obstacle. A 21% increase may not seem like much when you're landing on a long runway, but it can make a critical difference at a short field or one where conditions are marginal. Now let's go back and take another look at our formula, which is that rollout distance is increased by the square of the ratio of the actual touchdown speed to the normal landing speed. Using that formula again, a touchdown made at 60 knots, which would be 10 knots faster than the normal landing speed, can result in the use of 44% more runway on rollout. And if that's not bad enough, flying it on at 20 knots above the normal touchdown speed can add a whopping 96% to your rollout, which might just put you in the next county, and could also be justification for a go-around. You know that old fairy tale about adding 5 knots on final approach for the spouse and 5 knots for the kids and so on? Well, I'm not going to ask for a show of hands to see who among us has ever landed 20 knots too fast, for whatever reason. But I'll bet that after seeing those figures, you'll sure think twice about doing it again. Now, do you remember back in part 1 when we told you we would explain the difference between aim point and point of touchdown? Well, this is it. So here goes. First, let's redefine the two. The aim point is your imaginary bullseye on the runway. It's the reference point you put at the end of your selected glide path. Point of touchdown, on the other hand, is the spot on the runway where the airplane actually touched the ground. A main objective of every landing exercise is to roll rubber at the intended point of touchdown, rather than allowing yourself to land long. In order to learn more about how we can do this consistently, we must take a close look at the last steps in the landing process, which are the flare, the touchdown, and finally, the rollout. The flare, or roundout as it's sometimes called, is the period of transition from approach attitude to landing attitude. For most aircraft, flare begins at about the time the airplane enters ground effect, which should be slightly before you reach your selected aim point. As we mentioned in part 1, ground effect is the height equivalent to about 1 wingspan. The length of time it takes to flare can be affected by such variables as aircraft weight, rate of descent, the power being carried, aircraft configuration, pilot technique, and so forth. During the flare, you are constantly changing pitch attitude as airspeed and height decrease. And when your airspeed finally dissipates to a point at or just above stall, the airplane settles onto the runway. Now you can begin to see why the aim point and the touchdown point are always some distance apart. If the proper approach speeds have been flown and your piloting techniques and procedures were on target, your point to touchdown will be right where you intended it to be. That is, at your intended point of touchdown. If, on the other hand, your piloting techniques and procedures are still on the money, but you happen to be carrying excess airspeed at the moment of flare, your airplane will float, continuing to glide above the runway until that excess airspeed has dissipated. As a result, you will overfly the intended point of touchdown and land long. Obviously, you can see that in order to make precision landings, you've got to be on the ball. And that goes double at a busy airport, because traffic flow may dictate the need for you to have to carry extra airspeed on final, or shift your aim point. You see, you're almost never the only airplane out there, and you've got to remain flexible to work within the system. A controller may ask you to stay well above the normal traffic pattern, or to maintain cruise speed until you're on short final. And then he might come back and ask you to land short and clear at the first available intersection, things that you were taught not to do back in flight training. Or he may ask you to deliberately land long, maybe because he wants to keep the parallel taxiway clear or to minimize your time on the runway. In any event, always be prepared to compensate your approach techniques to help maintain the flow. But never forget that you are the pilot in command. Don't be intimidated. If you feel uncomfortable about doing something or can't comply, say so. Express your pilot prerogatives. Now, how many of you are aware that landing at less than the maximum landing weight can also result in your landing long? Well, it can. And it will. As you'll recall, a little earlier in this program, we said that if you don't have a published approach speed, you should carry 1.3 VSO on short final. Well, that's true, but it's vital that you understand the definition of VSO in order to avoid landing long. So let's go back and take another look at the definition first. For the purpose of this discussion, VSO is the calibrated power-off stalling speed of an airplane in its landing configuration, and usually with a forward CG. Please note, however, that I did not say anything about max landing weight in the VSO definition. VSO is not your stall speed at max landing weight unless you happen to be at max landing weight at the time. At any other time, you'll be at something other than max landing weight, which usually results in a lower VSO. Now, as long as you're approaching the runway at max landing weight, 1.3 VSO at max landing weight is okay. However, landing at anything less than the max landing weight can be like flying a different airplane. Let me give you an example of what I mean. All large aircraft, that's all aircraft that weigh more than 12,500 pounds at takeoff, have detailed and very specific instruction on landing speeds, or VREF speeds, for reduced landing weights. Take this heavy jet, for example. In a few minutes, it's going to land at its maximum certificated landing weight. By that, let's say that we're talking about 350 passengers, lots of baggage, and tons of fuel. Now imagine that same heavy coming in from a ferry flight and landing with no passengers, no baggage, and only 1 hour of reserve fuel. It doesn't take a lot of figuring to realize that the airplane in the second example could weigh 100 tons less than the max weight airplane, and that there will be a significant difference in VREF speeds between the two. Now, since the laws of physics apply equally to small airplanes, they too must have different approach speed for different landing weights. And flying the appropriate approach speeds for these reduced landing weights is a necessity to avoid landing long. Does an airplane stall at a lower airspeed when it weighs less? Sure it does. The lighter the airplane, the lower the stall speed. And what you want to do, of course, is touch down at or just above stall speed when you land. Let's go through the mechanics of a typical full stall landing to show you what I mean. First, let's say you just took off with a full load of people, baggage and fuel, realized you left something like your credit card back at the FBO, and immediately turned around to come back for it. What we're doing here is setting you up on final approach while you're still at max landing weight. Now we're going to ask you to come in over the fence at 1.3 VSO at max landing weight. Okay? As we explained a few minutes ago, you have to complete the transition from the approach attitude to the landing attitude. Everything is going by the book. The approach looks great, and your touchdown's right where you intended it to be. No overshoot, no white knuckles, no sweat. Now let's make everything exactly the same, except that in this second example, you've been tooling around by yourself all day, so your landing weight is much lighter. But you still opt to carry the same short final approach speed as before, 1.3 VSO at max landing weight. And lo and behold, your intended point of touchdown whizzes by beneath you. Why? Because you're still floating in ground effect. And why are you still floating in ground effect? Because you came in light, at a lower landing weight, but you were still flying your approach based on VSO at max landing weight. So your airplane flew merrily down the runway. You see, your airplane's stall speed was lower because the plane was lighter. And your airplane floated in ground effect because it was still approaching its actual landing speed and just wasn't ready to land. The point we're making here is that 600 pounds can be just as significant a difference to a small plane as 100 tons can be to a heavy jet. And there you have another important lesson about landing, that you must learn and fly the appropriate approach speeds for different landing weights. Incidentally, were you aware of the fact that some general aviation airplanes have the color-coded arcs on their airspeed indicators painted in calibrated airspeed values, while others display only indicated airspeeds? It's a fact. You see, starting in the latter half of the 1970s, most aircraft were built with airspeed indicators that had color-coded arcs marked in indicated airspeed rather than in calibrated airspeed. Calibrated, of course, is indicated airspeed corrected for position and instrument error. Now, how is that significant? Well, just as an example, it means that if you want to calculate your approach speeds and you're flying in one of these latter-day airplanes, you've got to go to the handbook and check the stall speed tables to find out what VSO is in calibrated airspeed. Then you must multiply that value by 1.3, 1.4, or whatever, and convert back to indicated to find out what speeds to fly. To do anything else would create the potential for flying an approach at much too slow an airspeed, because the airspeed instrument error in some aircraft can be significant at the lower speeds. This whole subject is something else that we've put in your handout for a more detailed explanation, along with a rule of thumb formula for calculating approach speeds at reduced landing weights. There's one more thing I'd like to mention before we move on to another subject, and that is that the manufacturer's recommended final approach speed, or if not available, 1.3 VSO, is an airspeed to be flown on short final only. Remember, however, that until you're on short final, you're probably still maneuvering. By that I mean you are banking and turning, and you want to be at a higher airspeed than 1.3 VSO to make sure you can handle those banks, as well as any turbulence and wind gusts with a comfortable margin. Wind, by the way, is another major factor that can result in landing long. To determine your landing rollout distance in the presence of a wind component, consult your POH. But did you know that a light headwind isn't always a factor in computing landing distance? That's right. As a matter of fact, a rule of thumb is to treat a headwind as calm if it's less than 10% of the actual touchdown speed. Here's an example. If your touchdown speed is 50 knots, you can treat a 5-knot headwind as a no-wind condition. But take heed, we just said actual touchdown speed. Don't confuse that with your final approach speed. On the other hand, a tailwind can have a significant impact on your landing rollout distance in an adverse way. Again, you should consult your POH. However, landing with a tailwind has the same effect as carrying excess airspeed on final. It compounds your landing rollout distance by the square of the ratio of your tailwind component plus your actual touchdown speed over your normal touchdown speed. That is, of course, if all other factors are equal. For example, if your normal touchdown speed is 50 knots and you fly 10 knots faster to compensate for gusty wind conditions and also land with a 10-knot tailwind, your landing rollout distance will be almost double your normal rollout. Now look, if all that sounds too complicated to figure out in the pattern, just don't land downwind. Anytime the headwind component includes a gust factor, you may choose to carry extra airspeed on final approach. You'll remember that we said this is one of the few times we recommend doing so. One recommended technique is to divide the gust factor by 2 and add it to the normal approach speed. All you need to remember is that whenever you modify your approach speed, you also invalidate the landing distance stated in your handbook. So watch out.
Wind check, please.
Wind 190 at 15, gusting 25.
In this instance, we chose to add 5 knots, half the gust wind component, to our approach speed. See how it works? By the way, your handout has more information about gust factors. Now, let's move on to a discussion about landing on inclined runways. If you've been flying for a while, you've probably experienced that strange sensation associated with landing up or down an incline. FAA utility airport design standards allow maximum grades of up to 2%, or about 1.2 degrees of slope. At such airports, runway slope is a comparatively minor factor. Runway slope can be a real factor, though, if the airport you're landing at has not been built to government standards. So a word to the wise, get as much information as possible about destination airports before flying there. If you do land on an inclined runway, the rule of thumb is to always land uphill, wind and obstacles permitting. But check Unicom first, and always announce your intentions. Another of the 8 factors affecting rollout distance is density altitude. As stated earlier, density altitude is a combination of pressure altitude and temperature. And since these 2 variables can be read directly from the altimeter and the outside air temperature gauge, or OAT, Pilots' operating handbooks now provide either tables or graphs which allow you to determine the effects of density-altitude in one step. You should use these tables and graphs to establish the effects of density-altitude on aircraft performance. Older aircraft publications use a two-step method that accomplished the same thing. These publications provide a means of using pressure, altitude, and temperature to calculate density altitude first, and then to determine its effect on aircraft and engine performance. To be technically accurate, humidity is also a factor in density altitude, but since its effects are minimal for landings, it is not normally considered. Density altitude doesn't have a whole lot of impact on landing rollout, the way it does on takeoff performance. But pilots should never forget that high, hot, and humid means higher density altitude, higher true airspeeds, and therefore longer runway requirements for takeoff as well as for landing. High, hot, and humid also means there may be a potential need to lean the fuel-air mixture on landing to assure good engine performance, both on the approach as well as during the go-around. On the other hand, when elevation, temperature, and humidity result in a low-density altitude, a rich mixture will give you the best engine performance. Check your POH for specifics on performance, but figure on adding about 5% to the landing roll for each additional 1,000 feet of density altitude, all other factors being equal.
Let's continue now with our look at the 8 causes of landing long. Runway surface can make a big difference to your landing rollout because it plays a tremendous role in braking effectiveness. A dry concrete runway offers one of the best braking surfaces, while a runway covered with wet, clear ice provides one of the worst. Most other surfaces and surface conditions fall somewhere in between. In Part 3, we'll discuss in detail how to land on icy, wet, or snow-covered runways. Right now, however, let's limit our discussion to talking about proper braking techniques on dry surfaces. Once you touch down, proper braking is the key to coming to a full stop within a specified distance. But since landing performance figures are determined by experienced pilots under ideal conditions using maximum braking with brand new brakes and tires, and since you just might not have quite as much going for you, treat the published landing distances as minimum distances and allow yourself an extra margin. In order to achieve the most effective braking, don't begin to brake as soon as you touch down. You see, right after touchdown, your airplane is still producing lift, and a premature application of brakes does little more than leave 2 expensive skid marks on the runway. You shouldn't really begin to apply brakes at all until after all 3 wheels are on the ground and the airplane is slowed enough so that it's at least 25% below touchdown speed. As a matter of fact, if you look at this graph, you can see that aerodynamic drag is the biggest single factor in slowing the aircraft during the first quarter of the speed decay. You can also see that brakes become increasingly effective as airspeed and lift decrease. There are 2 ways to increase braking effectiveness on landing rollout. First, some pilots' operating handbooks indicate that retracting the flaps will decrease lift, thereby putting more weight on the gear. It's really best, however, to wait on flap retraction until you're well clear of the runway so you can divert your attention to your checklist. Then you can concentrate on identifying the flap switch or handle properly, rather than taking the risk of retracting the gear by mistake. Look at it this way. By delaying flap retraction until well clear of the runway, you will even out your pilot workload responsibilities and avoid confusion. Besides, Taxiing to the hangar with your gear up requires one hell of a lot of power. Once the nose wheel is on the runway, the safest way to increase braking effectiveness is to hold the wheel or stick full back as you firmly and smoothly apply the brakes. Back pressure is held primarily because, with heavy braking, the airplane tends to lean forward, putting a greater portion of the weight on the nose wheel. Use of up elevator or stabilator counters this reaction and puts weight back on the main braking wheels where it belongs. In tail draggers, it also reduces the chances of dinging the prop or flipping over as you brake. Now, landing on a grass runway is a great way to preserve your tires, but remember, grass is also a much less effective braking surface. Wet grass or frost-covered grass is even worse, so beware. Also, to avoid surprises on your landing rollout, be sure to check your brake pedal pressure before you enter the traffic pattern. If your brakes feel mushy or soft or floorboard, you know you've got a problem. The best action to take in such a situation is to arrange to land on a longer runway and, if necessary, at another airport. Also, make sure that you land as nearly into the wind as possible. It's very poor technique to learn about brake problems when you're on rollout. Best braking is always achieved when the wheels are in what's called an incipient skid condition. In English, that means that just a little more brake pressure would lock up the wheels entirely and make them slide down the runway. In an incipient skid condition, the wheels are turning, but with great reluctance. Whatever you do, though, don't lock the wheels. Locked wheels mean skidding down the runway on tires that are not turning. Braking effectiveness drops radically when tires skid, not to mention damage done to the tires themselves. Larger aircraft are equipped with anti-skid equipment that, when working properly, assures that the wheels can't be locked and the tires won't skid. By the way, intermittent braking serves no useful purpose when the objective is maximum deceleration, because the periods between maximum brake application produce only slight cooling. Airline flight crews routinely inspect the condition of their tires prior to each flight. It's also a good practice for your personal airline. And don't just check the tires for depth of tread and proper inflation. Also inspect for bald spots, cuts, dry rot, and so forth. You know, it's amazing how many blowouts and other tire problems can be traced back to an inadequate pre-flight. Getting back to operating procedures, though, let me test you with this one. You should always stay right smack dab on the runway center line during your landing rollout. True or false? Well, it's false. At airports equipped with centerline in-runway lighting, it's actually best to keep your nose gear a few inches to the left or right to avoid excessive wear and tear, as well as possible nose gear damage. But at all other airports, it is best to stay right on the runway centerline. Now, earlier we mentioned that runway length is also a factor in landing long. Oh, I know that you're not going to land a jet on an 1,800-foot runway. At least I hope not. But did you know that you can turn a 2,100-foot runway into an 1,800-foot runway just like that? That's right. One way, of course, is to have a displaced threshold. But you knew about that, didn't you? However, did you know that if you fly a non-standard VASI, and that's the homemade variety, that even if you're flying the right airspeeds, you'd also better have a good idea of where the airport operator has located his aim point for you. You see, a displaced aim point could have you going off the end of the runway at the other end by suckering you into landing long. And since government publications do not provide specific information about non-standard VASIs, it's up to you to know what you're up against. And that completes our discussion of the 8 most common contributors to landing long. To review, we talked about mastering airspeed control, landing at less than max landing weight, and the effects of wind on the landing rollout. We also looked at density altitude, runway slope, surface, and length, and talked about proper braking techniques. Only once so far have we mentioned the practical alternative to a long landing, and that is the go-around or balked landing. A properly executed go-around is one of the best accident avoidance procedures available to pilots, even though it's one of the least used. But when it's not executed properly, it too can result in an accident, and a much more serious one than just landing long. So let's talk about how to do a go-around and how to do it right. Official reports concerning accidents resulting from a go-around frequently cite pilot indecision as a contributing cause. What usually happens is that the pilot is so fixated in his attempt to make good a bad landing that the idea of scrubbing the whole thing and going around to try again doesn't even enter his mind. Or if it does, he thinks of it too late. You see, the whole motivation during an approach is to land, not to go around. But every second given to a bad landing can mean double trouble to an eventual go-around attempt. First of all, you're wasting valuable braking surface, but valuable height is also being lost by delaying the go-around decision. If there's any question about making a safe touchdown and rollout, take the airplane around and do it early. Don't delay. Treat the go-around as a normal procedure rather than an abnormal or emergency one. World War II prop planes taking last-minute wave-offs from aircraft carriers provided those on the flight deck with some pretty spectacular maneuvering. Once again, the lesson: plan ahead. Regardless of aircraft type, weight, or class, there's one cardinal rule when flying an approach, and that is, be prepared to go around. Because even the best approach can result in the need for a go-around due to factors completely and totally beyond your control. So always be mentally and physically prepared to go around. Now then, there are many different terms used to describe the go-around, including, of course, go-around, wave-off, aborted landing, rejected landing, and balked landing. But they all mean the same thing, and that is that the pilot, for one reason or another, has to break off the approach and try again. Now, before we talk about the how-tos of going around, we have a suggestion. Experienced pilots always decide in advance on a go-around point on the runway. If they haven't touched down when they get to that point, they simply take it around and do it all over again. You may want to adopt this policy for yourself as well. And remember, at a high-density altitude airport, or one where there's rising terrain, you might actually put your go-around point somewhere before you get to the runway. Now, in general, when executing a balked landing, we suggest that you look closely at these following steps. Seriously, though, we want to give a good sequence for a properly executed go-around. But first, I just want to remind you once again that your POH, or owner's manual, should really be your Bible for this, so please review it periodically. Now, here are the steps. Power, of course, is the single most essential ingredient. Therefore, every precaution must be taken to assure the availability of power when it's needed. For example, when you're landing at an airport with a high-density altitude, make sure your mixture's leaned as necessary to provide for maximum power. Why? Because you might need all the power available for a safe go-around. And remember, one of the key phrases here is high density altitude, because density altitude is the only altitude that's important to your engine. Look at these two airports. One's high, the other's low. But they both have the same identical high density altitude. Some piston-powered aircraft will also require the application of carb heat at reduced power settings. If you don't do this, you might find yourself with an iced-up carburetor and no power. And your checklist will probably call for you to go to the high RPM position if you have a variable pitch prop. One other part of your pre-landing routine should be to get in the habit of saying to yourself, "Now let's see, if I have to go around, this is what I'll do." And then you review the actual steps you'll take, because if you do go around, you'll only have time to do. You won't have time to plan. I'd like to point out that what you're actually doing here, of course, is taking the first steps toward a possible go-around before setting up your initial approach. And that's a good thing to do. Now that you're both mentally and physically prepared, you continue your initial approach with your hand on the throttle, knowing that you're ready to go around if you need to. And if you do, don't hesitate. Do it. Apply full power and adjust the airplane's pitch attitude. That's right, do it. And once you've made your decision, stick to it. Don't vacillate. Even if it begins to look like you might be able to make it after all, stick to your decision. Take it around. You have an advantage that space shuttle pilots don't, so why not use it? Too many airplanes have been lost because the pilot changed his mind back again and tried to land after all. Now, when you actually take it around, first and foremost, fly the airplane. Forget the tower, forget the unicom, forget the passengers. Sure, they've had a lot of coffee and need to get on the ground. They always do, but just fly the airplane. Make sure that you've applied full takeoff power and that it stays there. Engine vibration can cause those power controls to inch backwards, or a defective gauge or sensor can make you believe you've got full power when you don't. And always push the carburetor heat or alternate air to the full off position. In a go-around, either carb heat to off or full power may come first. But if full throttle is added first, it must be a smooth application to assure engine response. If you've got a turbocharged airplane, watch that manifold pressure red line. And if you're flying a turbine, monitor those engine power gauges. And make sure you trim the airplane to maintain proper pitch control, or else... This is what we call the prelude to a hammerhead stop. So remember, until you've adjusted your trim, be prepared to apply some pretty heavy forward pressure on the controls to maintain the proper pitch attitude for climb. And use your attitude indicator to help you establish and maintain a positive climb. But if you're VFR, don't fixate on the gauges. Use outside references. Now, once the airplane is firmly under control, ease the flaps back up in increments, further adjusting pitch and trim as necessary, and retract the gear only after a positive climb is established. As your speed increases, let it continue to accelerate past the best angle, then to the best rate of climb. Adjust cowl flaps as necessary, and keep an eye on your track over the ground, staying slightly to the right side of the runway so you can watch for departing traffic. Now communicate. Remember, control first, then communicate. There is no exception to this rule. However, if you're at an airport with a busy control tower, it's prudent to tell the tower what you're up to as soon as possible, but never at the risk of compromising your safety. When you're back at pattern altitude, power can be reduced and you can set up your next approach. Take your time, though, and make sure you pay particular attention to your checklist. You see, A go-around always creates stress, regardless of how proficient you are at it. And it creates extra stress when the weather's bad or when you're low on fuel. Either way, you could be approaching a work overload situation. More than one pilot has landed gear up after a go-around because he was under stress and didn't use his checklist. If you pull this stunt, you'll find out that even your best mic technique won't bring you back to superhero status either. You know, there's an old saying, there's them that have and them that will. You've got to work at not falling into that latter category. I guess it's just like everything else in flying. Only practice makes perfect. And only through repeated practice can an unfamiliar task become a familiar one. You see, as you gain proficiency through practice, you're also gaining experience, and therefore, you're less likely to be under stress when you encounter the real thing. So, what's the message here? Review. Then, practice your go-around procedures so that when you really do have to make one, you'll be on top of the airplane, rather than the other way around. In summary, we've discussed factors that influence a pilot's decision to go around and offered some practical tips. Key points included: be mentally prepared for a go-around on every approach. And when in doubt, go around. And if you do go around, stick to your decision. Also, maintain control and don't forget to trim. In every go-around situation, these are your priorities: add power, set pitch attitude, fly the airplane, clean it up, then communicate. And before beginning your next approach, use your checklist. You have been distracted. In Part 3 of On Landings, we'll talk about dealing with landing gear emergencies, give you some proven tips about landing on wet, icy, and snow-covered runways, and shed some light on landing at night. See you then.